So if we think about the properties of these surface waves, so we're just thinking about the properties of a basic gravity wave propagating out in deep water. The key properties that quantify it are there's an amplitude, there's a wavelength, and a frequency of the wave. Okay, so amplitudes in meters, wavelengths also meters, and then frequency we usually express as an angular frequency in radians per second. And so here's your wave over here propagating along. The wavelength is the distance between one crest and the next. And then the wave height is the difference between the trough and the peak. And that wave height is twice the amplitude. And so you can see how these properties appear in a mathematical expression for the wave. So a typical propagating wave like this is just a sea surface height perturbation, which we call eta, equaling an amplitude by some sinusoidal form. And so here's the frequency here. There's also this other property in here called K, and K is what we call the wave number, and it's defined here. So it's 2 pi over the wavelength. And so that's what appears in the expression for the wave. The other properties, derived wave properties, we've also already introduced is the steepness, which is the ratio of the height to the wavelength. And the other key one is the period, which is 2 pi on the angular frequency. So that's how long, if you're sitting at a point, say here, you're sitting at a fixed point, how long does it take for that wave to propagate past and you to get from one crest to the next crest as the wave propagates past? Okay, so these waves, of course, propagate along the sea surface, but that doesn't mean that everything is confined to the sea surface. So they propagate along the sea surface, but as the surface sloshes up and down, of course, there is motion in the ocean below. And that motion in the ocean below can be expressed in terms of a horizontal velocity that's in the direction of wave propagation and a vertical velocity orthogonal to it. And they take the following form if our surface height took this form. So they're also sinusoidal, and you'll see that the horizontal is a sine and the vertical is a cos, which means they're out of phase. And in fact, what that means is that particles in the ocean beneath the wave are actually moving in these circular patterns. And you can see that in the diagram here, and also in this movie, which shows a propagating wave in the laboratory through a fluid that has a suspension of particles. And if you look as the wave propagates, you'll see that these particles travel in circles. The other key thing to recognize here is that the amplitude of the particle motions, and so the amplitude of these velocities, decay as you go down through the ocean. And so you can see there's a very clear bottom of the wave, which is shown in this diagram, and you can also see in the movie. And it turns out that this bottom is about half the wavelength in depth. So this, from the surface to the wave base, is about 1/2 of a wavelength. And that's wrapped up in this exponential decay factor here, this e to the kz out the front of these velocities.